Hi, Assalamualaikum warahmatullahi wabarakatuh, and a very good afternoon, everyone. So, today we are going to have our extra class, or what we call it substitute class, class ganti. Because last time we have missed our class, so today is the day where I want to do the class ganti for you guys. So, we have finished chapter 5. Yay! So, today we are going into a new chapter, which is chapter 6. Chemical equilibrium. Sorry, I just typo just now. It's not chemical, it's a chemical. CHE. Okay, I'm sorry. So, and today we are going to look at the first subtopic 6.1, dynamic equilibrium. So, in today's subtopic, the learning outcomes that we are going to look at is one. We are going to explain the following terms. First, we are going to explain the reversible reaction. Second, dynamic equilibrium, and the third is law of mass action. And we are going to state the characteristics of a system in equilibrium. And lastly, we are going to interpret the curve of concentration against time for a reversible reaction. Okay, so without further ado, let's get started. Alright, so when we go into chemistry, a chemical reaction, there are two types of chemical reaction. The first one is non-reversible reaction, and the second one is reversible reaction. Okay, all right. So, most of the case, the chemical reaction is a reversible reaction. However, maybe some of the reaction may have this kind of non-reversible reaction. Okay, so let's see what's the difference between non-reversible reaction and the reversible reaction. So, non-reversible reaction is the reaction that proceeds in only forward direction. So the reaction only occurs from the reactant forming a product. Okay, so the reaction will stop when the reactant is completely converted to product. Okay, however, for the reversible reaction, the reaction is proceed in both forward and reverse direction, meaning that the reactant can form a product and a product can form a reactant back. So that is the difference between reversible and non-reversible reaction. However, in this topic, we are going to focus on the reversible reaction. Okay, so the reversible reaction, for the reversible reaction, at some point there will be a state where this chemical reaction achieve a dynamic equilibrium. So we are going to look at that right after this. Okay, so let's move on to the next part. Okay, so let's look at this curve. So we are going to interpret the curve of concentration, reactants and products against time for a reversible reaction. So let's look at this example. We have 2SO2 gas react with oxygen gas to form 2SO3 gas. Okay, so this 2 is the reactant. So this 2 is the reactant. And this is the product. Okay, so let's see the explanation. So let's look at the curve, the graph. Okay, for the reactant, we see here that at the beginning of the reaction, the concentration of the oxygen and the sulfur dioxide decreases with time. So, rate of forward reaction decreases over time. Nampak? Dia kat sini. The concentration of oxygen and SO2 gas decreases over time. Okay. So, the concentration of product SO3 increases with time and the rate of reverse reaction increases. Okay, why is that so? Because once the product is formed, once the SO3 gas is formed here, this SO3 gas will start to decompose back into a reactant. Okay, so maksudnya So at the beginning of the reaction, the reactant will produce product. So that is why the concentration of the reactant decreases over time. And the forward reaction decreases over time as well, because makin lama concentration makin sikit kan, makin decreases. That's why the rate of forward reaction decreases as well. Okay, however, at some point after the product is formed, this product will then decompose back into a reactant. So this is when the rate of the reverse reaction increases. Okay, so now the flask contain the mixture of SO2 gas, oxygen gas, and SO3 gas. Okay, however, upon reaching this point, TA, or we call this dynamic equilibrium, okay, so upon reaching this time, so at this point of the time, the concentration of SO3 gas, oxygen gas, and SO2 gas remain unchanged. It remain constant for both reactant and product over the time. Okay, so the concentration of the product and reactant remain constant not because of the reaction has stopped, but because of the state of equilibrium has already achieved by this reversible reaction. So what does it mean by that? So it means that the rate of the forward reaction from reactant to product is proceeding at an equal rate with the rate of reverse reaction from product to reactant. Okay, so I have included in this note on the explanation of this graph. So right here, it has stated everything that I have said just now. So at the beginning of the reaction, concentration of reactant decreases with time and rate of forward reaction decreases. Concentration of product increases with time and rate of reverse reaction increases. So once the product is formed, SO3 gas decomposes to SO2 and O2 gas. So now the flask contains a mixture of SO2, O2 and SO3 gas. So that's the explanation at the beginning of the reaction. Then you have to explain at the dynamic equilibrium TA. So at dynamic equilibrium, the concentration of reactant and product become constant and no further change in concentration for all the gases with time. The reaction does not stop, but a state of chemical equilibrium exists when both forward and reverse reaction are proceeding at equal rate. Maksudnya kadar forward reaction, the rate of forward reaction is equal to the rate of reverse reaction. So when the forward reaction and the reverse reaction are proceeding at an equal rate, so there is no change in the concentration for reactant and product. Okay, that's why we said that the system has achieved a dynamic equilibrium or equilibrium. Okay. So reminder here, okay. Upon reaching a state of equilibrium, there is no net change in the concentration of reactant and concentration of product. But it does not mean that reactant punya concentration is equal to the product punya concentration. Okay, the concentration of the reactant is different from the concentration of the product. So the state of equilibrium just show that the concentration of the product and reactant remain constant. Okay, itu je. Bukannya dia cakap the concentration of reactant is equal to the concentration of product. Bukan. Okay, so understand the difference between that. Alright, so next, we are going to look at the types of equilibrium. So there are two types of equilibrium. The first one is physical equilibrium and the second one is chemical equilibrium. So what is physical equilibrium? So physical equilibrium is the reaction that does not involve any changes in chemical composition, but just changing in the state of matter. So chemical composition ni macam mana? Concentration, dia punya color and everything. So physical equilibrium, dia tak change in chemical composition. It just changing in the state of matter. Okay, for example, here we have the vaporization of water. So water here, so in picture A, it says that the liquid water molecules leaving the rate of liquid water molecules leaving is greater than the water vapor molecule returning to the liquid phase. Okay, dekat sini water yang banyak vaporize into water vapor instead of water vapor returning back into liquid phase. However, after some point, bila dah cukup, dah banyak dah, bila the system is at the equilibrium where the rate of forward reaction water to water vapor is equals to the rate of reverse reaction water vapor to liquid water. So now the liquid water molecules leaving is equal to the water vapor molecule returning to the liquid phase. So we said that this system has achieved a physical equilibrium. So now H2O liquid the rate of reaction or forward reaction from water liquid to water vapor is equal to the rate of reverse reaction of water vapor to the water liquid. So that is how so that is the explanation for the physical equilibrium. So now, what is chemical equilibrium? So chemical equilibrium is a reaction that involves changes in chemical composition such as colors, such as the concentration is changes. So now let's look at the example of this reaction. N2O4 gas decomposed into 2NO2 gas. So if we look at the picture here, diagram here, at first, at A, this is the start of the reaction. So the color of the gas is colorless. However, now at B, the N2O4 started to decompose as NO2 gas. So now the mixture becomes pale brown. So now the N2O4 has started to decompose to form 2 mole of NO2 gas. Okay, at C, now the mixture has reached the final color, reddish brown, and it has reached the equilibrium state. Why? Because dekat point B ni, once dia form product, some of the product will then combine back to form N2O4 gas. So now, when the rate of reverse reaction is equal to the rate of the forward reaction, at C and D, now the color of the mixture has achieved the equilibrium, where the rate of the formation of N2O4 to form NO2 gas is equal to the rate of NO2 gas forming N2O4 gas. So now the concentration and the color of the mixture remain constant. So at C and D, we can say that the reaction has achieved the dynamic equilibrium, okay, where the rate of forward reaction is equal to the rate of reverse reaction. Okay, some note here. We can say that at equilibrium, the N2O4 molecules decompose as fast as NO2 molecules combine. So at equilibrium also, and the concentration of N2O4 and the concentration of NO2 remain constant, but bear in your mind that their concentration is not the same. Okay, so we have learned on what is reversible reaction. We have learned how to interpret the concentration against time curve, and we have learned about types of equilibrium. Now we want to look at the characteristic of a system in equilibrium. How can we know that the chemical reaction has achieved a state of dynamic equilibrium? So the first one we can know by observing the concentration of reactant and product. So for a system to be in a state of equilibrium, the concentration of the reactants and products are constant over time. So kalau the concentration of reactant and products are constant over time, that is one of the characteristic to say that the system is already in an equilibrium state. Second one is the rate of forward reaction is equals to the rate of reverse reaction. So this is also one of the characteristic for a system to be in equilibrium. And the last one is the reaction quotient Q is equals to the equilibrium constant K. So we can say that Q equals to K. So this reaction is in a state of dynamic equilibrium. So these three are the characteristic of a system in a chemical equilibrium. Okay, now we want to look at the law of mass action, or dengan kata nama lain, equilibrium law. So we can consider one of the general chemical equation here, AA plus BB forming CC plus DD. So this is the reactant, this is the product, and the small letter is the stoichiometric coefficient, which usually represent the moles of the reactant and product. So, to find the equilibrium constant K, we should know the basic where the concentration of the product must be divided with the concentration of the reactant. So that is why we have here C to the power of small c times the concentration of D to the power of small d over concentration of A to the power of small letter A times concentration of B to the power of small letter b. So C and D is the product and A and B is the reactant. Hence explain why the concentration of product over concentration of reactant is equals to equilibrium constant K. Okay, so now, so dekat sini dia kata, the concentration at equilibrium is used to determine K. So we must use the concentration at equilibrium to determine the equilibrium constant K. So now, let's look at the example. We have N2 gas plus 2H2 gas to form 2 NH2 gas. So to write the equilibrium constant here, product over reactant, so the product is NH3, so NH3 square bracket to the power of 2 divided by concentration of nitrogen gas times the concentration of hydrogen gas to the power of 3 here. Okay, so this is how you write the equilibrium constant punya expression. And of course, if they give you the value, you can substitute the data into this concentration so that you can find the value of equilibrium constant K. Okay, so actually that is all for the chapter 6.1. It's very simple. We just need to know what is the meaning of reversible reaction, what is the how to interpret the curve of concentration versus time. You have to understand the characteristics of dynamic equilibrium, and lastly, you need to understand the expression for equilibrium constant K. Okay, so now it's a quiz time. So what you need to do is you need to scan this QR code and answer 3 questions regarding this subtopic. It's a very easy question and a very direct question. I hope that you will get all full mark for this quiz. Okay, so we are going to continue with chapter 6.2 after this. So please stay tuned. Okay, and yeah, for your tutorial question, you just have to answer question number 1 for now, because that is all for the question for chapter 6.1. Okay, so other than that, we are good to go, and thank you for watching this video. And Assalamualaikum. Bye-bye.